students, welcome back to our course Environmental Modeling and Simulation. In today's lecture, we are going to start our discussion on groundwater. We are interested in how the water flows underground, and we are also interested in how the contaminants that are injected or find their way into groundwater get transported, get dispersed into the groundwater. Now, groundwater moves slightly differently than the water that moves above the surface of the ground. So, when we talk about groundwater, we need to first understand how the groundwater flows. Unlike surface water, which flows in open channels, groundwater flows through the pores of the soil. So, let's say these are soil grains. As they are packed together, they will have pores between them, and it is in these pores here, it is in these pores that the water will travel through when the groundwater is flowing. This feature of the soil grains to have pores between them is referred to as porosity. Clearly, the porosity of the soil will affect the rate at which water flows. So, this is the first term that we need to understand when we are trying to understand the flow of groundwater. The other thing is we need to understand why the groundwater flows. In our previous lectures, we talked about air contaminant flowing through air, and the reason for the bulk transport of these contaminants was wind. So, if you remember in the previous lecture, we had a chimney which was releasing air pollutants, and the air pollutants were being carried away by the wind. So, if someone is downwind, they might get exposed, but if someone is upwind, they will not get exposed. While wind is the carrier and the cause of bulk transport of contaminants in air, we need to understand what is the major driver of transportation, bulk action in groundwater. In groundwater, it is hydraulic gradient. Now, let's try to understand what hydraulic gradient refers to. Hydraulic gradient is basically the difference in the head divided by the distance between the 2 points. So, for example, let's say this is our surface. Now, I have made it dramatically inclined. In most of the country, this is not the case. So, let's say this is our groundwater, and here is our groundwater table, and then here we have an impermeable layer. So, this is semi-confined aquifer, it is confined on the bottom. This is water level, and this is ground level. So, if we take 2 points here, let us say point A and point B, this is the height of the water table here, let us call it H1, and this is the height of the water table at B, let us call it H2, and let us say the distance between point A and point B is R. Then the hydraulic gradient between point A and point B will be given by the difference of the heads divided by the distance. So, hydraulic gradient would be del H by the distance between the 2 points A and B, which in this case will be H1 minus H2 by R. Now, hydraulic gradient drives the movement of groundwater, which means the water wants to move from high pressure zone to low pressure zone. And remember, the water travels in through the pores. So, it does not flow like a river, but it sort of flows like a river, but it flows through the pores. It does not have open space to flow through. So, in the case of groundwater, we assume that the flow of water is linearly proportional to the hydraulic gradient, which is the difference in pressure heads divided by the distance between the 2 points. Now, this is an assumption of linear relationship between the flow and the pressure gradient, the hydraulic gradient, which may not always be true, but it is a pretty good assumption. But this also has many other assumptions. The first assumption is that the pores are completely saturated. So, if you are above the water table where the pores are not completely saturated, then this linear relationship between the flow and the hydraulic gradient will not be valid. The second assumption is that the flow is not turbulent. In rare cases, when groundwater is having a turbulent flow, then this model will not be valid. The other assumption is that the soil does not have fine grain. With fine grained soil, the porosity may become very low, in which case this model will not work anymore. But when we are below the water table, when the pores are completely saturated, when the soil has decent porosity, the grain size is not very small, and the flow is not turbulent, this is a pretty good relationship. This is also known as Darcy's law, that the flow rate is proportional to dH by dr. So now let's put the proportionality constants. So here, this is what we have. Flow is proportional to dH by dr, and we add a proportionality constant Ka dH by dr. We need to add A, area. If you look at the units, you will see that this is distance by distance. So it's unitless effectively. Here we have K, which is hydraulic conductivity. Hydraulic conductivity depends upon the soil, the geometry and the fluid that is flowing through the soil, and then this is our flow rate in SI units or any other units that we are using. Okay, this is known as Darcy's law. This is valid, remember, when the flow is not turbulent, when the soil is completely saturated with water, and when the grain size is not very fine. Now let's say we have groundwater, and the groundwater has undergone some kind of contamination. So once again, this is our impermeable bottom layer. This is our water table, and then this is our soil. So below the saturation zone, this is the saturation zone, okay? So it's a water table. And let's say this is the height h1. At r distance, we have height h2. And this is our r, the distance between 2 points A and B. This will tell us the hydraulic gradient, dH by dr, is given by h1 minus h2 by r. So we know the hydraulic gradient, we know, let's say, the hydraulic conductivity of this aquifer, and we know the cross sectional area. Then we can find out the flow rate. Now let's say a contaminant has been injected here at the point A. Now this injection can be a one-time thing. Let's say it's like a pulse. It was injected and then the injection stopped. Or it could be a continuous injection. The contaminant is continuously being injected. Now in this case, we want to understand how the contaminant is flowing along with groundwater. Now remember, groundwater is flowing in this direction from higher pressure head towards lower pressure head. Intuitively, we know that the contaminant will be transported in the direction of groundwater. Now, if you remember our air pollution model, the Gaussian plume model, the contaminants were transported downwind in the direction of wind. Here, instead of wind, we have the flow of groundwater. Now, if we make few assumptions, the first assumption is that the contaminant is undergoing plug flow. So if we make this assumption that the contaminant is undergoing plug flow, which means the contaminant moves through the groundwater in the direction of the flow of groundwater like a plug, it's not mixing with the plugs in its neighborhood. The second assumption that we make is that the groundwater is traveling with contaminant, or in other words, contaminant is traveling with the groundwater. Now, with these two assumptions, this would be a very easy model. We just have to write our plug flow model and we can see how the contaminant is traveling. But let's look into these assumptions slightly more deeply. The first assumption is saying that contaminant is undergoing plug flow. What it means is that the contaminant is not mixing with its neighboring plugs. which also means that there is no diffusion happening. Because remember, diffusion will happen regardless of, as long as there are no physical boundaries, regardless of the overall direction of mass transport, diffusion will happen in all directions. Now here we are assuming diffusion does not happen, which may be a valid assumption given certain conditions are met, but which may not be a valid assumption when, let's say, the groundwater is moving very slowly. In that case, diffusion is important. Now another assumption that we typically make in case of groundwater is that the aquifer is shallow enough. The aquifer has limited height, which means that we can assume the vertical mixing of the contaminant is uniform. So what we do is we can essentially reduce the three-dimensional movement of contaminant through groundwater into a 2D system, because we are assuming that the vertical mixing is perfect. So the concentration at this place at the top is same as the concentration at the bottom of the aquifer for a given plug. So now we can make this a two-dimensional model and only work in y and z axis, x axis, and forgo the z axis. This is how we reduce a three-dimensional model into 2D. Now again, this may not be valid for certain aquifers, especially when the aquifers have higher dimension in the z axis, but for typically narrow aquifers, this is a pretty good assumption. Okay, now let's understand what difference does our first assumption make to the flow. Now let's say this is our aquifer and the water is flowing from left to right. Yeah. By the way, the water is flowing between these two layers. So I just put the arrow on the top to show. Let's say when the water flows like so, on x-axis we are plotting time, on y-axis we are plotting concentration of the contaminant. So let's say at a given time t1, the concentration of contaminant is very high. As time progresses, the concentration will remain where it is and the plug will move like a plug. There is no mixing happening. So if I use the highlighter to show you the contaminant, this is the contaminant here, and with time the contaminant moves further down. So we see it's moving like a plug, like a vertical plug. Now if it is not acting like a perfect plug, if there is dispersion happening, and now dispersion, remember, includes both bulk action and diffusion. So plug is only talking about bulk action. What I'm saying is if there is diffusion also, which needs to be incorporated, then if at initial time, let's say t1 or t0, this is how the contaminant looks like, then over time as the contaminant moves, it will have a profile something like this. So you see now the contaminant has spread out. It has diffused in y and x direction. Remember, in z direction we are assuming that there is no, it's already perfectly mixed. There is no diffusion happening because the aquifer is not very big in the z axis, in the z direction. But you see here the diffusion will make sure that it's happening, the diffusion is happening in x and y direction. There's another feature of groundwater transport that we need to look into. So far we have looked into dispersion and generally the plug flow nature of the groundwater. We have looked at porosity and why porosity is important. The next thing we need to look at when we talk about contaminant transport in groundwater is retardation. The principle or the cause behind retardation is sorption of the contaminant to the soil. This is very important term here, sorption. So as the contaminant moves through the soil, there's a good chance that some parts of the contaminant will get sorbed into the soil. So remember, the groundwater moves through the pores of the soil. It is in close contact with large surface area of the soil grains, and some level of sorption of the contaminant will happen to different parts of the soil in the surface of the soil. So what this will do is it will make sure that as the contaminant moves forward, so as the contaminant is moving forward, whether without diffusion or with diffusion, some concentration of the contaminant will be remaining behind because it is still sorbed with the soil. So let's say here I injected, just at T1 I injected some amount of contaminant, then I stopped injecting, it was a pulse injection. with the flow of groundwater, let's say it is undergoing diffusion, so there is dispersion. This is how the concentration profile looks like. As the contaminant moves forward, it will leave behind trace of contaminant, and as the water in the soil sorbed to the soil, not necessarily adsorption, but sorbed to the soil, and as the fresh water moves trailing behind the plug or the contaminant, some part of the sorbed contaminant, so let's say this is the soil, and these are the pores between them. So these are soil grains, and then there are pores between the soil grains through which the contaminant is spreading or flowing through the water. Some part of the contaminant, let me use yellow color, some part of the contaminant is sorbed on the soil particles. So as the contaminant in the water moves forward and the fresh water comes in contact with these soil grains that have sorbed contaminant in them, then some of the contaminant will come in the groundwater, which will also move forward. So instead of moving like a plug like so, the contaminant again spreads out and it moves slowly compared to what it would have moved if there was zero sorption. There is a trail, it leaves a trail behind. So this is the effect of retardation. Now retardation basically tells me that there is some relationship between the concentration of the contaminant which is sorbed to the soil and the concentration in the water. Now if we assume a relationship between the concentration of contaminant in the soil and the concentration of contaminant in water to be a linear relationship, then what we can say is that the concentration of contaminant in soil and ratio of contamination in ratio of the concentration of the contaminant in soil and water is a constant. This is where we introduce a new constant for you. It's known as retardation coefficient, which is very important when we are modeling the groundwater transport. Okay, the other thing we need to understand is the relevance of groundwater models. Typically when we talk about groundwater models, we are either injecting some waste into the groundwater and we want to see how that waste is spreading, or we are injecting some kind of radioactive material or some kind of stable isotope which can spread through the groundwater and then give us information about groundwater flow, aquifer morphology and other information that we need to know about our groundwater transport. Or we are injecting some kind of compound, some kind of oxidant or chemical that can help us remediate a contaminated aquifer. The second kind of scenario is when instead of injecting, we are extracting the groundwater. So let's take a look at this condition. So let's say this is our groundwater table. Somewhere here is our surface water. Not surface water, sorry, ground surface. This is our water table, and then somewhere here we have an impermeable layer. Notice I like to keep the bottom layer as an impermeable layer because it makes modeling much easier, but this is not always going to be the case. If your aquifer is an open aquifer, it is not confined at the top, not confined at the bottom, we can no longer ignore vertical dispersion. Some water will move here, some water will eventually find its place in the unsaturated pores or partially saturated pores of the soil. So right now we are making an assumption that the bottom layer is impermeable layer and the plug is vertically mixed perfectly. So we can treat this like a 2D model, which is not always going to be the case. But let's say this is the second scenario where we use our groundwater models, and this is the scenario where we are pumping out the groundwater. So let's say we have a well here and we are extracting the groundwater at the flow rate Q. So Q is the flow at which we are constantly pumping the groundwater out, which is a very common practice across the globe, definitely in our country too. What happens is that as we pump the water out, the water table distorts and it looks something like this. So what happens is the water table falls, and we can assume that on both sides, left and right side of the water table, this fall is symmetric. So even though my drawing is not perfectly symmetric, but the fall is perfectly symmetric. So now let's say we have height h here and we have height h1 here, and the distance between them is r. The hydraulic gradient, see the water, now this overall hydraulic gradient is not as important as this local hydraulic gradient, because this is driving the flow of the water towards the pump, right? The water table has fallen in the neighborhood of the pump, so the water is rushing towards the pump. So we are going to look at the gradient here. So let's say this is H. Here we have H1. So now we know what dH by dr is. Again, subtraction of these H minus H1 by R. Okay, so this is our hydraulic gradient. We know that the flow rate is proportional to the hydraulic gradient, and then we have this is, by the way, Darcy's law. I should have shared this earlier. Assuming that there is a linear relationship between the flow of groundwater and the hydraulic gradient is Darcy's law, and then we have hydraulic conductivity multiplied by area dH by dr. We can apply this system, to understand how the water flows when we are pumping groundwater up, because now the water is not flowing in the direction of overall hydraulic gradient, but in the direction of the local hydraulic gradient created by the action of pumping the water up. So in this scenario, let's take dq, right? So we are taking a small strip here. So now I want to understand what is the flow rate here. So let's take a point which is r distance away from the pumping valve, and the height of the water table at r distance is given by singular h. And notice that this at r distance the height h will follow a circle. So if you are looking at the top view from here, what you will see is something like this. Here is our pump which is pumping the water out, and then at r distance, if you draw a circle around it, the water table in this circle is h. Okay, the rate at which the water is flowing through this h circle of h water table height r radius can be given by dq is equal to k into area. So the area will be the area of this cylinder of height h radius r, and then we know the area of the cylinder will be 2 pi r into h, and then we have dH by dr, which is the gradient at h. Now we are going to integrate from this h, let's put it capital H, where the water table is at its usual height, and then the h where the water table is at lowest height h1, and we can integrate this using that from capital H to small h as the limit of integration for h, and including the actual distance where this depression of the groundwater table begins, from there all the way to the pump as the limit of integration for r. Now to integrate this is very simple. We need to separate the variables. So let's bring r on LHS left hand side and keep h on the right hand side. What we get is so h we are integrating from h to h1, and r we are integrating from r to r1, right? So we know where the depression in the water table begins, we know what's the height before the depression begins. By the way, we are referring to this as depression. This. In fact, there is a technical term for it, it's called the cone of depression. Cone of depression, because if you look at it, this is actually a cone of radius r, and this maximum differential is its height. Okay, so when we integrate this, we'll get So Q is given by K pi h1 square minus h square divided by natural log of r1 by r. Now if I know what my height should be around the height of water table around the cone of depression at the center and at the edge of the cone of depression, if I know the size of cone of depression I'm willing to have, so R1 and R, and I know the hydraulic conductivity of the soil, I can figure out what flow rate is perfect to pump from the groundwater to achieve a particular cone of depression. The other thing is, if I'm pumping the water and I know at the rate at which I'm pumping the water, so Q is known to us. So Q is known to us. I see the cone of depression, I can trace it. There are a lot of ways to do tracer studies and to figure out how large and how what's the shape of the cone of depression, how it looks like. So if I know the features of the cone of depression like R and H, then I can use that information to figure out the hydraulic conductivity of soil. In fact, this is one of the ways in which we try to figure out hydraulic conductivity of soil. Okay, now students, let's go back to our contaminant. So if you go back to this figure here, the contaminant is flowing through the water. It's undergoing retardation because as it flows through the groundwater, it's sorbing with the soil. It is also moving forward, so there is bulk action. Let's write down these conceptually. Yeah, so what I want to do in the next lecture is I want to make a model for groundwater transport, a general model, and I want to show you how it may look like under certain circumstances when we integrate it. So, in summary, students, when we are modeling the transportation of a contaminant through groundwater, there are four phenomena that we need to pay particular attention to. The first, as we have discussed, is diffusion. So, one thing you need to remember is that in diffusion, we are talking about Fick's law. And at steady state, the Fick's law states that the flux due to diffusion, will be equal to diffusivity constant and the concentration gradient. So, this is in x direction. Similarly, we will have in y direction and in z direction. So, these terms need to be incorporated in your mass balance for diffusion. The next is dispersion or bulk action, movement due to bulk action. So, let us say advection. Now, this is when the flow of the fluid, in this case the groundwater, is transporting the contaminant from one end to other. So, this would be the way to incorporate this in your mass balance would be to multiply the velocity in the particular direction with the concentration at a given point. In x direction it is Vxc, in y it would be Vyc, and then in z it would be Vzc. Typically the convention is to use u, v and w instead of Vx, Vy and Vz. Okay, the third factor, which is incredibly important and peculiar to soil, is sorption of the contaminant in soil. And this sorption results into the phenomena we observe as retardation. Now, depending upon how the sorption is happening, whether it is linear, non-linear, or there is no sorption happening, the retardation looks very different. So, retardation can be linear and it can also be non-linear. And the retardation effects that we will see will depend upon whether it is linear or non-linear. For example, if there is no retardation, then the concentration of the contaminant will look like this. It will have a very nice bell curve distribution, but now because of retardation, it will look like this, and we are looking at linear retardation. So, it is still peaking in the middle, but it spreads out because of retardation, because of sorption to the soil. If we are talking about non-linear sorption, then we might see distribution of the concentration that does not resemble a bell curve, does not resemble a normal distribution, Gaussian distribution. In that case, it is non-linear sorption. In later classes, when I talk about isotherms for adsorption and absorption, we'll briefly go through how linear and non-linear absorption and adsorption look like. The fourth factor, which is essential when you are modeling groundwater contaminant transport, is degradation of the contaminant. Many of our groundwater contaminants do degrade over time by microbial activity. Not all of them, but many of them do. Even those that do not degrade, they might change their oxidation state to a state that is less soluble and less mobile. So degradation also needs to be included. Now degradation will, let's say first order degradation. So you'll have a first order decay constant and then the concentration of contaminant. Since it's degradation, you'll have minus sign that will be included in your equation, in your dynamic equation. Zero order, then we are just looking at degradation that is independent of C. So we'll have just the degradation constant. Of course, the units would be different. And if you have second order, then again we'll have Kc square. So this is zeroth order degradation, first order degradation, and second order degradation. When you put these four things together, diffusion, advection, absorption, which results in retardation, and degradation together, you will have a pretty good, robust fundamental to start your groundwater, to start your modeling of contaminant in the groundwater, how the contaminant is spreading and what its fate is going to be. Alright students, this is all for today's class. In the next lecture, we are actually going to put this conceptual model down as a mathematical model, and I'm going to show you two instances of what we get when we integrate that mathematical model. We are also going to discuss some assumptions that are required to make sense of that mathematical model. Thank you and see you in the next lecture.